Hello, welcome to this course on computational commutative algebra. I am Manoj Kumini. And I teach at Chennai Mathematical Institute. So what is this course about? This is meant to be an introductory course in commutative algebra. However, there will be an emphasis on computational aspects. Hence, in addition to doing the typical topics that are taught in a first course in commutative algebra, we will also try to understand the algorithms behind computing things about rings and modules using a computer. And therefore, some of the theorems that we prove in these lectures may not be as general as that are typically taught in a commutative algebra course. However, we will try to understand what is going on in a computer when it tries to compute various things about ideals or modules. So why do we care about computing things? It is an easy way to study examples. To construct examples and also sometimes give an idea on how to solve problems. This is the reason why there's an increasing interest in learning computational techniques in commutative algebra and similarly with an intersection with algebraic geometry. So all of these things we will learn using a computer algebra language called Macaulay 2. Which is freely downloadable from the web. So here are the references. Our primary reference, there will be two of them, would be this book by Cox, Little and O'Shea. Then this book by Eisenbud. And we will also occasionally refer or it might help you occasionally to refer, if this is the first time you're seeing these topics, to look at Reed's undergraduate commutative algebra. And the software that we will use is, as I mentioned earlier, Macaulay 2, which can be downloaded from its website, www.macaulay2.com, or it points to a much longer URL, which is from the University of Illinois. And if you do not want to download it and just want to run some simple programs or few commands for the program, there are places on the web where you can do it directly, and links to multiple such sites are available on this URL. Okay. So what is commutative algebra? It is the study of commutative rings. And helps also of ideals. It's the study of modules over them. And also applications. Traditionally, from the 19th century, questions in commutative algebra, or the importance of looking at some of these questions, came from studying questions in algebraic geometry. also algebraic number theory. And increasingly to combinatorics. And also algebraic statistics. These two topics are relatively, applications to these two topics are relatively more modern. And applications to the last two topics typically are related to the computational aspects of commutative algebra. So in these lectures, so this is lecture 1. In part 1, today's lecture, we will just do basic definitions, etc. In part 2, we will do this in Macaulay 2. However, in future lectures, we may not make a distinction. As we discuss topics, we will also look at some examples in Macaulay 2. So what's an example of a commutative ring? The most basic example is Z, the ring of integers. What does that mean? It has two binary operations. So what is a binary operation? So this is a function f from a set x to the Cartesian product of a set x with itself to it. So such a thing is called a binary operation, and Z has two binary operations that are of interest to us. Addition, which we denote by a plus. And what does that mean? For all integers n and m, we can take the sum, that's also an integer. And it also has multiplication, which we denote by a dot or just omit it. And now, what are the properties of these operations? Both operations are commutative. That is, for all integers, if you take the sum n plus m or m plus n, these are the same, and their product is the same. And multiplication distributes over addition. In other words, for all integers m and for all integers n1 and n2, if you take m, all of this inside Z, if you take m times n1 plus n2, this is the same as mn1 plus mn2. So this is another few more properties that are of interest to us in this thing. There is an additive identity That is, 0 has a property such that m plus 0 equals 0 plus m. This is okay because just saying it's commutative. Both of these things are the same value, m, for every integer m. And similarly, there is a multiplicative identity one, and that says m times 1 is 1 times m equals m for all m, integers m. So now we come to the definition of a ring. A ring R is a set with two binary operations. And we call it addition and multiplication. Addition, which we denote by a plus sign, and multiplication, which we denote by a dot or just omit. Typically, we will not write a dot, such that under addition, so if you take the set with this binary operation plus, this is an abelian group. It's an abelian group. Multiplication is associative. That is, if you take three elements in the ring, if you take the products, but remember we can take products of only two things at a time. So we can do it in two different ways. We could take the product of AB first and then multiply it by C, or we could take the product of B and C first and then multiply by A. And the associativity property says that these two things give the same result. Okay, so multiplication is associative. Multiplication distributes over addition. That is, A times B plus C is the same as AB plus AC. And we have not said that multiplication is commutative. So we must also consider B plus C times A. These two things may not be the same, but distributive property says that this is the same thing as BA plus CA. And these two statements for every triple A, B, and C inside R. Multiplication distributes over addition. Then there is we already said that under plus, the group, the set R is a group, is an abelian group. So it has an additive identity which we will denote. Okay. So we denote the additive identity, which we already know because it is a group, the additive identity by 0 sub R, and often this it will be clear that which ring we're talking about. So we could just write or just 0. Okay. Multiplication distributes over addition, and there exists a multiplicative identity which we denote by 1 sub R, or just 1, if there is no confusion as to which ring we are talking about. And so what does this mean? This means that m times 1 is same as 1 times m. This is m for all m in R. Okay. So this is a set with two such operations with these properties is called a ring. Definition. A ring is said to be commutative if multiplication is commutative. Remember, addition is already commutative by definition. So let's look at some examples. The ring of integers that we said is a ring that we saw already. Then the set of rational numbers the set of real numbers the set of complex numbers. These are also commutative rings. We can, with the usual addition and multiplication operation. And in addition to being rings, these are also fields. That is, every non-zero element has an inverse with respect to multiplication. Or in other words, if you take the non-zero elements of these sets and take the multiplication operation, they will be in these cases it will be an abelian group. So these are all commutative rings. So not all interesting rings are commutative. Non-commutative rings, there are important classes of non-commutative rings. So let's just, to become familiar with that, let's just use one example. And this is, we will not worry about them in general. Okay. So let R be a commutative ring. N a positive integer. By M and R, we consider the set of n. Consider the set of n by n matrices with entries in R. Usual matrix addition. matrix multiplication. With these two things, it becomes a ring. The additive identity is the zero matrix, and the multiplicative identity is the identity matrix, the n by n identity matrix. However, if n is greater than or equal to 2, then this is a non-commutative ring. So now we look at one more class of rings, after which we will look at some examples in Macaulay. These are called polynomial rings. So we start with a commutative ring. And we can take some variables, let's say x1 through xn variables. And then by this, we mean the set of polynomials in the variables x1 through xn with coefficients from R, and this is a commutative ring with usual polynomial addition and multiplication. And the additive identity is the zero polynomial. So this is the additive identity. Okay. And the multiplicative identity is the constant polynomial 1. And with these things, this is a commutative ring. Okay. So we will stop here now and we look at a few basic examples in Macaulay. So when you start at Macaulay, it depends on what you would see in a terminal, or the output will depend on how it's installed, what operating system it is, etc. Or are you running it on the web, or are you running it locally, etc. So here I just run it on a terminal and I just show you the screenshots of what one would see. And when I run it, I'll get a line which says this is version 114. And this is the input line. This is the input line. The one that starts with an I says you are in an input prompt, and it says the first input prompt. So now let's give something in the first input prompt, the first string that we know. We type ZZ here and then press enter. So here's the output. It says the first output line. So input lines are marked with an I, output lines are marked with an O, and it says O1 is ZZ. That's just acknowledging what it understood. And then it says O1 is a ring. So here, this is the class of this object, and we don't need to worry about it a lot, but soon we will have to worry. When you look at various functions, we will have to see what the type of input is, what type of output is, and for that, at that point, we will have to worry. And Macaulay tells us each time, whatever it sees, what object, where is it coming from? Okay. So now let's do a few more things. Let's explore a few more things. So in the second line of our input, I just type 4, and the output is 4 itself. And that's because it understands this as an integer. Then I ask what x as a third input line, and it says x, and it says now it's a symbol, that it does not know where this x came from. Okay. Here it knew it was an integer. So now we look at rationals. So I type 4/1. So Macaulay computes and says it is 4. Now it says it is QQ. That's the set of rationals. And I ask, okay, this is something that we just saw. So we ask Macaulay QQ. Then it says, yeah, QQ, it is a ring. And this is the notation for the set of rationals. So whenever we are confused, we can ask for help. So now I type help QQ, and one has to press enter. Help QQ. So then it will just type a lot of help. I mean, it will run into multiple lines, so I'm not showing you what the output is. You can try this yourself. But essentially it tells you what are the things that you can work with. In Macaulay, with QQ, what are the things that you can do? It's a long output, so I didn't. Okay, so now we come to something new. So real numbers. I type 4.0. So it again says it's 4, but it's not just integer 4. It says it is a real number. RR denotes real number, but this time there's a difference. It says of precision 53. Earlier ZZ and QQ didn't say that, and so I type RR, and unlike a ring, it now says inexact field family. And the reason for this is, in finite precision, you cannot write all real numbers. So it's a family of, depending on the precision that one needs, RR is implemented as a family of fields, and here the 53 is the default precision, and it just shows that. Now I ask what is pi, then it says it's a constant. Then I ask what is II, that's also a constant. But what is II? Let's check. I ask II squared. So again, each input line, it will put something corresponding output, and then it will tell you where is the output living in. Or so II squared is -1, and this -1 is not the integer -1. It is considered as a complex number. And again, same precision, for the same reason, complex numbers cannot be written in infinite precision. And CC, again, it's an inexact field family, exactly for the same reason as RR is an inexact field family. Just to familiarize ourselves with more or usual functions, simple functions, I ask 2, okay, 2 is an integer, that's all it says. Then I ask square root 2, this is the square root command. Then it outputs a real number and says now that output is in class RR and of precision 53. The default precision of reals is 53. Now I ask ZZ mod 17. We know that this is, we expect, the way we would do it on pen and paper, this is to denote the residue class of integers mod 17. So, and it says it's a quotient ring. So I have not yet defined a quotient ring, but it just says here is a ring which is of class quotient ring. Okay. So we'll worry about quotient rings in the next lecture. But we know that this is the same thing as a finite field of 17 elements. And the command to construct a Galois field, a finite field, is GF, both uppercase. So I ask GF17, and it says it's a Galois field. Now this is where the idea of class comes in. We ask, okay, OO with 3 equals OOO. Well, what does this mean? OO means previous output. OOO means the output before that. So on line 17, OO denotes O16, and OOO denotes O15, and so it's asking whether GF17 and ZZ mod 17 are the same, and it says it's false. And that's because they are objects in turn. One is a quotient ring, the other one is a Galois field. Okay. So one has to worry a little bit about these things when you write code. Okay. So now I consider a polynomial ring with variables x and y with integer coefficients. So now it says R is a polynomial ring. X, now earlier when we asked x, it just said symbol. But now if you ask x, it says x is in R. Okay. It has found a place where x lives. I now define a different ring. same variables x and y, but coefficients are from rationals. Again, it's a polynomial ring. And now I ask what x is. It says x is now in S. It has forgotten the R. How do I go back to R? I type use R. Now it's gone back to R. Now if I ask what x is, it will interpret x as an element of R. So these are some issues that one has to worry about when one writes code. Otherwise, some unexpected results may come. Okay. So how do we know what are the variables in a ring? So in a polynomial ring. So I ask gens, so for generators, gens R. It gives x and y with curly brackets, and it says it is list. Okay. So right now, so lists are lists of elements with bounded by curly brackets. One can also get this information using a command called vars R, but now it puts the same output but in a different fashion. It writes it as a matrix. So these distinctions, we will not worry about it at this stage, but one should keep in mind that such distinctions do exist. Okay. We can ask where do the coefficients of these rings come from? So remember, R was a polynomial ring in x and y over z over integers. This was a polynomial ring in x and y over the rationals. So if you ask coefficient ring of R, one would get ZZ, and it's a ring, and coefficient ring of S, QQ, and that is a ring. Okay. So this is the end of the first lecture. Okay. In the next lecture, we will talk about homomorphisms, ideals, quotient rings, etc., and slowly we'll try to develop more things about rings, simultaneously understanding how these things are computed in Macaulay. At least how to compute it in Macaulay 2, not what is going on behind it. That will take us a few more lectures. Okay. So please redo these commands in the Macaulay code that you saw. The lines that start with an I, enter that command. You don't need to write the I and up to the colon, just the command is enough. And see what the output is, and make sure that you understand what the output is saying. Or at least, if you don't understand, take a look at their help pages. So Macaulay. So hereafter, I will start writing M2 to denote Macaulay 2. There is a help command to see help in the terminal itself, and sometimes it will run into many pages, and you will lose what we have computed before it. In that case, there is a help command to see it in a browser if you're working it on a local terminal. This won't work if you're doing it on the web. But on the web, so it's view help command. H is an uppercase in this thing. So use these two things to understand, at least try to explore what Macaulay 2 is. See you in the next lecture.